Hello everyone, welcome to power system classes. So in the last class, we were looking at the inductance and capacitance of transmission line. Okay, so we were looking at the inductance and capacitance of transmission line, and I have discussed a lot about the inductance and capacitance also. Today we will continue some discussions on inductance and capacitance, and then we'll be moving towards some of the other aspects of transmission. Okay, so we'll be looking at the capacitance. Okay, so yesterday I have derived the equations for capacitance, the last class. You can also check that one. I hope this is working. Okay, so I forgot to share the screen. Okay, so just going to start. Okay, so it's okay. Like I didn't say, like, you know. So okay, inductance and capacitance. So yesterday we have derived the equations for the capacitance, and today we will be actually saying, okay. So if you look at the capacitance, so yesterday when we derived the capacitance, we have considered two capacitance, right, like this. Okay, but if you look at the, like, you know, if you look at the practical scenario, what is happening is that these two capacitance are there, but beneath these there is something known as an earth is there, right? Something known as earth is there. Okay, so so we have to consider the capacitance with respect to earth, because why we need to consider this is that when we apply the Gauss law for finding the, like, you know, so that one, so that is surface integral d dot ds equal to q, or we find that like, you know, that d equal to q by 2 pi epsilon 0 x, right? So I have derived all these things, right? So epsilon x, so this epsilon is actually for surrounding the whole of earth, surrounding whole of universe. Okay, so what we assume that the whole of the universe there is only one epsilon x, but if you think like this, so here there is something like a different epsilon, and here also this is earth, right? So earth is highly conductive, and so, like, you know, the property of the air and the property of the earth is actually different. So that means there is something, like, you know, something different. So how can we model this? So if you look at the earth, so the earth is normally at V equal to 0 potential, right? So that means now all the electric field, actually if you check there, the electric field actually comes here and actually it passes, okay, like this. And V here is basically 0, okay. So, but if you think there, because it is not exactly 0 here, so you want to make this as 0. So in order to make this as 0, we actually like, this is the electric field actually coming from this particular thing, and this is the electric field. Like, if you assume that this is the positive conductor, and this is the negative conductor, right? So the electric field actually comes from here, and actually it also comes from here, right? And electric field actually goes to negative. So something like this. So it will be actually coming, and so we need to make this particular point 0. That is the boundary condition it has to satisfy, right? So what is the boundary condition it has to satisfy? This boundary should be, because earth is always at the potential 0. So we need to make this potential 0. So what basically what uniqueness theorem states that, I hope you know the uniqueness theorem electromagnetics, right? So what uniqueness theorem states that if there is some combination of charges are there, so if there is some combination of charges are there, and that combination of charges makes all the boundary conditions. I'll write in horizontal. It is what is something known as a uniqueness theorem. Okay. Uniqueness theorem basically states that assume that we have some kind of a charge combination. This charge combination makes some kind of a boundary condition, like then what uniqueness theorem states that if the both charge, if all the boundary conditions are actually satisfied, then the charge combination or that potential is unique. Okay, that is we want to find a charge combination such a way that if that charge combination satisfies this V equal to 0, then that means that particular solution is unique, or that is the exact solution. Okay. So we need to now make a charge combination such a way that the potential at this particular boundary is 0. So that is basically the root of method of images. Okay. So what is the method of images means is that this method of images is actually coming from the uniqueness theorem. Okay, or something like if you go to the higher classes, you can see actually there is something known as like charge simulation method or something, where we use a similar kind of a concept. Okay. Where we make the boundary condition satisfy. So if the charge combination satisfy the boundary condition, then that charge combination is unique, or that is the exact the potential will be the exact of this one. Okay. So now we need to make the charge combinations unique. So for that, what we will do is so we will put, if this is plus Q, we will put something like a minus Q. Okay. So that means now these two distances are same, right? If this is at a height of h and this is at a height of minus h, so the center, sorry, this is also h, it is like measured from the ground. That's why I put minus h. So that is this distance is same in both the directions. That means the potential in the middle will be always 0. Okay, so this charge combination actually satisfies the potential at this particular point 0. Similarly, there is a minus Q here, right? So the image of this will be actually something like a plus Q here. Okay, so that means here also the distance is half, so that the center of this will be always a 0 potential. That means this charge combination satisfies this boundary condition, right? V equal to 0. So that means now we can actually apply the now the solution of that problem and solution of these problems are unique, or both are same. So that's the basic idea of a uniqueness theorem. Okay. So now we can use the capacitance. So instead of 2 charges, now we have 4 charges. So what is VAB? The distance of D, and this is basically, this distance is basically 2h, right? So what is CAB? Capacitance between these two lanes. That can be written as, no, I will first write VAB, then from VAB we can find this capacitance. Okay, that is basically Q by 2 pi epsilon ln D by R. That is due to this one. Now okay, now due to this one will be minus Q by 2 pi epsilon ln R by D, right? That is basically due to this one. Now we can find due to this one. That is, okay, I will just write it here. Just wait for some time so that it will get settled. Okay. That will be minus Q by 2 pi epsilon, Q by 2 pi epsilon 0, or we can assume it to be epsilon 0. Okay. Epsilon 0 ln root of 4h square plus 4h square plus d square, right? That is this distance. So this capital D, sorry, this capital D square, right, by R, by the distance between these two, that is 2h. Now we can write due to this plus Q. So that will be plus Q by 2 pi epsilon 0 ln 2h divided by root of 4h square plus d square. Right. So just opposite of this will be actually coming here. Now we can actually do all the manipulations, and we will get VAB. You can write VAB. So VAB will be equal to Q by pi epsilon 0 ln. So Q by pi epsilon 0 ln 2HD divided by R into root of 4h square plus d. Okay. So you can actually find this. So if the h is very, very large, that means this will be very, very small, and h square will be taken out, h and h will get cancelled, and 2 will be also cancelled. So it will be similar to the old one, Q by pi epsilon ln d by r. Okay. So this is capital D. Okay, sorry. So if the h is very, very large, then we can say this 4h square will be larger than this d. So 2h will be coming out, and 2h and 2h will get cancelled. So basically Q by pi epsilon 0 ln d by r. This is the one what we obtained in the last class, okay, due to the capacitance. So now the effect of capacitance is that now the now from this we can find what is the capacitance, C equal to Q by V. Okay, I think you can find this. So capacitance per unit length will be Q by V. Right. So we can find from this one. We can find. Okay. So I hope there will be some modification with the capacitance due to the presence of ground. Okay, so that is very important. So if we want to model the capacitance in the presence of earth, what we want to look is we want to look at the method of images. So how is the method of images is basically coming from? Method of images is basically coming from the theorem which is known as the uniqueness theorem. Okay, that is, if the original problem, the boundary condition is satisfied by a combination of some charges, then the solution of these two will be unique, and that will be the real solution. Okay, so that is the, so we have the original problem. What was the original problem? So original problem is like this, plus Q and minus Q, and boundary condition is V equal to 0. So we want to find the capacitance between these two. This is the original problem, right? Capacitance we have to find out. So now what uniqueness theorem states that we don't know the charge combination. There will be some kind of a charge combination, and that if that particular charge combination satisfies this boundary condition, then the solution of that particular charge combination, we can use that particular kind of charge combination as the unique solution for this original problem, right? So both will be unique and both will be the same. So that is basically known as the uniqueness problem. That is, if there are two solutions, so the ideal thing, like, it is coming from something known as a Poisson's equation. So the Poisson's equation states that if there are two solutions for a Poisson's equation, then the two solutions will be same and both will be equal. Okay, that is the basic concept of a uniqueness theorem. That is, there are no two charge combination possible which gives you same boundary condition. That is basically the definition of uniqueness theorem. No two charge combinations or no two potentials like charge combinations are possible which gives you same boundary conditions, right? Or same potential distribution, you can write. Which gives you same potential distribution. Which gives you same potential distribution, right? If two charge combinations gives you same potential distribution, that means those two charge combinations are unique, that two are equal. So similarly, our potential distribution is something like this. We have to get a zero potential at this particular point. Okay, so that is basically the meaning of uniqueness theorem. Okay, now we can go to and we can write all these things, and from here actually we can go to another aspects of transmission line, that is basically known as the corona. Okay, so I will just go back here. You can write all these things if you want, and I will wait for 1 minute so that you can actually write all these things. Okay. So these things, they might ask you to derive the, because like if you go to some interviews like a BARC or something in power grid, they will ask you to derive the effect of capacitance due to the presence of ground. So you have to explain all these things. Okay, then that will give you a good good impression in the interview panel. Okay, because all the interviews will be like paper pen. They will give you paper and pen, and you have to write all these things. Okay. Okay, now we can actually go to the next part, that is corona. Okay, so now I hope everyone knows what is a corona, because everyone's life is affected by corona. We are not talking about that corona. We are actually talking about corona in power transmission lines. Corona in power transmission lines. Okay. So I think almost everyone has seen at least corona in their daily life, right? If it is something like a rainy season, if you go near to the towers in a rainy season, you can hear something like a hissing sound, right? Something like if you go near to the tower, you can see this hissing sound is due to corona, right? That is, in that particular case, the visual corona is not present, but the corona has already started with a hissing sound. Okay, this is one of the things with corona. So what is basically corona means is, if the transmitting voltage is very high, so that means if it is a very high voltage transmission line, then the electric field caused due to this high voltage will be, this voltage will be also high, right? So there is something known as an electric field. What is the electric field caused due to this particular high voltage? It will be very high, right? So this electric field, which results in ionization of the nearby air, right? Ionization of nearby air. That is, nearby air, there will be ionization. And this ionization of the air results in dielectric breakdown of air. Dielectric breakdown of air. Okay. So what is basically dielectric breakdown of air is that if you just assume that there are two electrodes here, and assume that these two are actually filled with air. Okay. So there is something known as a dielectric breakdown, dielectric strength. Dielectric strength is that at that particular, up to that particular voltage, it will act as a dielectric. So after that, it will actually starts conducting. Okay. So every insulator has something known as a dielectric breakdown strength. Okay. So after that, it will starts conducting. So that means what is the dielectric breakdown strength of air is 21.2 kilovolt per centimeter. This is RMS value. Okay. RMS value of AC value. That means if it is assumed to be 1 centimeter, so if you actually provide 21.2 kilovolt across these two electrodes, then there will be something known as a dielectric breakdown happening between these two, or these two electrodes starts conducting. Okay, you can see something like a conductor. So air is no longer an insulator after the dielectric breakdown. Okay, so now what happens is that this nearby air actually dielectric breakdown, that is, it gets lot of energy. Right? The nearby air will get lot of energy. So if you think about the air, there are actually lot of nitrogen is there. Like nitrogen is the most important component of an air. So that means there will be nitrogen molecules will be there. These nitrogen molecules get lot of energy, and it will actually go to the higher shell. After some, it will actually come back to the original position. At that particular point, there will be something it will emit some kind of an energy. that energy can be seen as light, and that is something you study in chemistry. So similar to that, if the ionization is becoming very, very large, we can see something like a glow near to the conductor. Glow near to the conductor. So what is basically corona means is, when the high voltage is applied across a transmission line, the electric field become very, very large. So this electric field causes ionization in the nearby air, and which causes a dielectric barrier or dielectric breakdown in the air, which results in a glow near to the conductor. That glow is basically known as the corona glow. Okay, that is basically in violet color. Color is almost similar to violet. Okay, that is the wavelength corresponding to the nitrogen. Okay, that's why we are saying a violet color with the presence of ozone. It produces ozone. Okay, produces ozone because ozone has a very good bleaching property. So if you go to some people who works a lot in high voltage, you can see that their hairs are actually almost white because this arcing will causes a lot of ozone, and ozone will actually bleach your hair. Okay, that is why we can almost all the high voltage engineers, they have something known as white hairs. Okay, even I was working for high voltage in last 4 or 5 years. Even my hair also started actually getting white color due to the presence of ozone. Okay. So, so what is the problem with this corona? The problem with the corona is that some part of the transmission energy is lost in corona. Right. There will be some kind of an energy lost in corona. That is, there is something known as an energy loss. Right. So there will be something like an energy loss. So that is unwanted, right? So there is some kind of an energy. There is already a transmission loss is there. So with the transmission loss, there is something known as an energy loss due to corona is there. So how are we seeing coronas? Corona can be detected by two things. One is hissing sound. Other is this glow, violet glow. Okay, so that means up to a particular voltage, after a particular voltage only, we can see the violet glow. That particular voltage is known as visual disruptive voltage or visual critical voltage. So only after the visual critical voltage you can see the violet glow. So the hissing sound actually starts much before the visual critical voltage. That is corona disruptive voltage. Okay, this is something known as a corona disruptive voltage. So corona disruptive voltage will be actually less than the visual critical voltage. So visual disruptive voltage, some people call it visual disruptive voltage. So visual disruptive voltage will be much larger than the this one. Okay, so I hope you understood what is it. So I think you can write all these things if you want. We can go to the so what is the critical disruptive voltage of air? That is the voltage at which corona occurs. Okay, this is the critical disruptive voltage of air. Critical disruptive voltage of air. Okay. That is normally called that as G. Okay, like some people call it as G. We usually call it as G. So the value of G is 30 kilovolt per centimeter peak. Right, 30 kilovolt per centimeter peak, or 21.1 kilovolt per centimeter RMS. If you multiply with root 2, we will get this particular value. Okay. So that is basically, this is at NTP. Okay. So NTP is normal temperature and pressure. That is 1 atm, 1 atmospheric pressure and 25 degrees Celsius. Okay. So this is the basic equation. Okay, for G. So that means a normal temperature and pressure. So I am just stressing again. If it is at normal temperature and pressure, this will be 21 kilovolt per centimeter. Okay, and if the temperature conditions are different, actually you will write in a different way. Okay, so visual critical voltage is something greater than the critical disruptive voltage. Okay. Now assume that at normal temperature and pressure, NTP, normal temperature and pressure, assume that our dielectric strength is G0. Okay. We assume that our normal dielectric strength is G0. Then there is a correction factor delta for any other temperature and pressure. Okay. There is a correction factor delta for other temperature and pressure. That is G equal to G0 into delta. Okay, G0 is this particular value. So that where delta can be evaluated as 3.92 B divided by 273 plus T. Okay. So this B is something known as the humidity. What is the humidity? Okay. And T is the temperature in degrees Celsius. So remember this. T is the temperature in degree Celsius. Okay. So these are the important things. Okay. I think you can just write down this one. Okay. Okay. Now we can look at the what is the disruptive critical voltage. Okay, or critical disruptive voltage, that is VD. How we can find the VD? Because I have already found that we only know the dielectric strength. Okay, that is G, that is voltage per centimeter. So if that is not for one unit, like we have to find out what is the disruptive critical voltage. Okay, that will be R, that is the radius of the conductor, G0. So let's wait for some time. So this will get it. R, G0, M0, delta ln d by r. Ln d by r. Okay, so what is this m0? M0 is something known as the sorry, d is the distance between the two. Okay, okay, write as the d here. D is the distance between the two conductors. Okay. Okay. So what is the M0? M0 is basically what we call M0. M0 is the smoothness factor. What we call M0? M0 is the smoothness factor. M0 is the smoothness factor. So the value of M0 can be 1. The value of M0 can be 1 for an extremely smooth conductor. That is not practically possible. And normally it will be between 0.9 to 9.3 to 1. Okay. This is the common value because there are some unevenness in the surface. Okay. 0.93 to 0.1 it will be there. For a standard conductor, it will be between 0.8 to 0.9. As standard conductor, it will be between 0.8 to 0.9. So this will be the thing for a standard conductor. So other D is the distance between the two conductors, like we are considering a double circuit transmission line. There is a positive thing is there and there is a negative. Okay. And each having a radius R. Okay. So that is basically VD. Okay. So one thing you can remember here is this G0 is given in kilovolt per centimeter, right? So that means if the R is also right, if you write R also in centimeter or also in centimeter, that means this both centimeter will get cancelled. So for while you are actually putting the values in the equation, you should remember this. You should always put everything in centimeter. Okay. So this since this is a ratio D by R, you can put both in meters or both in centimeters. That is irrelevant. Okay. So I hope you understand this part. Okay. So let's wait for some time. Let's get stuck. So this will be in centimeter. Okay. If you put everything in centimeter, then it will automatically works correctly. Okay. Now we can find the power loss. This is the critical disruptive voltage. Now we can find the power loss. So what is the power loss due to corona? Okay. So power loss will be, we write 240 divided by some textbook there are 242 into root of R by D into F plus 25 into V minus VD the whole square into 10 raised to minus 5 kilowatt per kilometer per phase. Okay, this is the total power loss. Okay, now we can check this is, you have to mug up this equation because there is no other way we can do this. So we can check what is the effect of frequency. So what happens if frequency increases? So if frequency increases, then power loss also increases, right? That's directly proportional. Then what happens if D increases? Okay, so if D increases, if you write the alt equation for VD, I'll just equation for VD here. So VD is basically R G naught M naught delta ln D by R, right? So if D increases, then VD increases, right? So if VD increases, then V minus VD decreases. That means PC now decreases, right? So if a conductor is having a large diameter, then our corona loss is basically small. Okay, so we need to make a large conductor. If the conductor diameter is very large, then this will be small. So this can be also say like the diameter is large, then electric field is small. Electric field is small, then PC is small. Okay, so this way also we can define this. So if the weather condition is very bad, so it is if the humidity is large. So if the humidity is large, then the delta will become large. Like then the VD will become from if the humidity is becoming large, then PC is also becoming large. Now the VD got reduced and V minus got increased, and so that the PC will now increase. Okay. The Raynaud's now also it will be increasing. So if radius increases, this is the distance between. Okay. So sorry, this is the distance between. This is not the diameter, sorry. The d increases, if the radius increases, then we can say electric field basically decreases, then corona decreases. Sorry, I have mentioned this. This is the distance between the two electrons. Okay. Now, the conductor is more and more smooth. Then what happens is that corona decreases. Right, corona decreases. Okay. So I will explain it again. What happens if frequency increases? So if frequency increases, then the f plus 25 is there. That will increase. Then power due to corona will also increase. So what happens? The distance between these two increases. If the distance between these two increases, then actually VD increases. For the disruptive voltage for the corona actually increases. Then V minus VD actually increases. So that and there is a D here. Okay. So that is basically the square term is there. So that will be dominating. So the PC will now decrease. So what happens if the humidity increases? If the humidity increases, then PC also increases. Then what happens if the radius increases? So if the radius increases, it's like this, so make it large. That means now what happens is electric field at this particular point decreases, right? The electric field at the particular decreases, then corona also decreases. Now what happens to a smooth conductor? Smooth conductor delta is 1. Okay, that means 240 delta increases. If delta increases, then PC actually decreases. That's why corona actually decreases. Okay, so actually we can check this. These are the important things what we have to consider. Okay, so these things are very important for the interview. They might ask what are the factors. Okay, so one of the questions they asked me, like when I was doing my IAC interview or IAC PhD interview, they were asking, is corona loss only applicable to AC, right? So everyone, like, this was a new question to me at that point. So I started thinking, because even if this PC is becoming like, we have to find the value of PC for F is 0. AC means, so if that's the DC, that means F is 0. So even if this F is 0, this F plus 25 is not 0, right? So there will be some value. That means PC is now not equal to 0. So for DC condition also, there will be something known as a corona loss is always there. Okay. So the corona is for both AC and DC. Corona is for both AC and DC. This is very important. Okay. So you can write all these things. Then actually we'll be going to the next point. Okay. I'll give you 1 minute time so that you can actually write all these things. Okay, now we can go to the next topic. Can you think about what's the advantages and disadvantages of corona? Okay. Advantages and disadvantages of corona. So the important question is whether is there any advantage for corona? Like, we already mentioned that corona has actually something known as a disadvantage is there. Okay. So is there any advantage? What are the, like, if so, we can. So one of the thing what I have mentioned earlier was if the corona is there in a conductor, that means the air near to this also becoming a conductive, right? So that means the effective area of the conductor is now increased. Effective area of the conductor is now increased, right? So why is it important? Why is this important? So if the effective area of the conductor is increased, that means the diameter is now increased, right? Effective diameter increased. So if you look at the capacitance, now the capacitance is now increased, right? So if the capacitance increased, then the time constant of the RC circuit of this particular RC will be now increased, right? So what happens if the time constant is increased? That means if assume that there is a surge actually going like this, okay, a steep rise. Now if it is traveling through the transmission line, then since the time constant is increased, we cannot have this kind of a response. So inside the capacitor, inside the transmission line, surge will be actually traveling like this with less steep. Okay, that means this dA by dt, if you look, or dV by dt, that will go to infinity, right? But here that is not exactly infinity. There is something like a positive value, which is less than infinity. So that means now there is not something like a sharp rise of the surge. Surge is the, like, the steepness of the surge is now reduced. Steepness of surge is reduced. Right. This is the one of the advantages of corona. What is the advantage of corona is that corona will actually increase the area of the conduction. If the area of the conduction is increased, then capacitance increases. That means time constant increases. So the time constant increases, then the steepness of the surge actually reduces. Okay. That means this is now less problematic to the equipments. Right. The dV by dt is infinity, then like it will cause a lot of problem to the electrical equipments. Now we can look at the disadvantages. First disadvantage I already mentioned, there will be energy loss. Right. There will be energy loss. Second disadvantage is telephonic interference, or if there is a nearby conductor carrying something like telephone line or something like carrying current or carrying information, there will be this electric field produced due to this corona will get interference with this particular line. So communication interface will be there. We won't get that perfectly. So that's why if you go or if you construct a home very near to the large transmission towers, your old CRT TV may not work properly, right? Because there will be some kind of interference will be there. Okay, that is the important part. So these are two problems. One is the energy loss, and second one is the telephonic interference or the communication interference will be there. Okay. So now what are the methods by which we can reduce this? So the first method is we can check larger diameter, or the radius should be very, very large. The radius will be very large, then I have already mentioned that the power loss will be very, very small. Then we can choose something like a hollow conductor, right? In hollow conductor, for same power, the diameter is basically large. Or we can take something like a bundled conductor. For bundled conductor also, for transmitting the same power as compared to this kind of a metallic conductor, the equivalent radius is large. Okay, that is GMR is always greater than R dash, right? So that's why this will be actually happening. Okay. So I think you understood what is basically meaning of the corona, and you can write all these things. I will wait for 1 minute. Okay, then we can actually proceed. Okay. Now we are looking at the last part of the transmission system. The last part of transmission system. That is basically the insulators. Okay. Basically insulators. So if you look at the transmission tower, what are the important components in a tower? Okay. First one is the conductor. Right. So if I draw a tower here, so this is the conductor. So first important part is the conductor. So the conductor is the one which carry the power. Okay. So second part is the tower itself. Okay, or the mechanical structure of the tower, which supports the conductors, or the which actually keep the conductors in suitable, supports the conductors in suitable height. Right. Conductors in suitable height. This much height is actually there. Okay. That is basically this one. Now the insulators. So what is the role of insulator? So insulator provides electrical insulation. So first role is to provides the electrical insulation also give a mechanical support to the conductor. Mechanical support to the conductor. Right. Now there are some other items, miscellaneous items. So there are plates, face plates are there. Then danger plates are there, which will be stick with this particular tower. Then something known as a lightning arrestor. On the top of the tower, there will be something known as a lightning arrestor is there. Then then there is something known as dampers are there. Mechanical dampers are provided with the tower, etc. Like these are the important part of a tower. Okay. If you look at and there is something known as an arcing horns. That will actually helps to protect the insulator. There is something you can see here like this. There is basically known as an arcing horn, okay, between the insulator. So this will get discharged first, without this. Okay, like this will actually create a single line to ground fault. Okay, if there is an arcing happening, this current will be flowing like this, and this will create a single line to ground fault. But what happens is that this insulator will get protected. Insulator will get protected. So that's why we are using something known as an arcing horns. Okay. So if you see a string of insulator, actually you can see the arcing horns. Okay, everywhere. That is the most important part in a this transmission system. Okay, so there is a tower, conductor is there, tower is there, insulator is there, and miscellaneous. Okay, these things are important. So what are the use of insulator is? It provides the electrical insulation. Then it also provides the mechanical support. Okay. So what are the next question is how an insulator is made up of? Okay. So the insulator is made up of something having a high resistance, right? Because it should act as an insulator or a dielectric. Okay. It should be non-porous. Water should not enter into it. Free from impurities. Because if there is some kind of impurities there, that will actually create a conduction. And cracks. There should not be any cracks. So the cracks will be a soft point for the conduction, or it will actually helps in the conduction. Okay. So this is the thing. And high ratio of flashover voltage, puncture to flashover voltage. So puncture to flashover voltage. Okay. These are the important thing you should know. So the most important thing what we use for actually making a insulator is porcelain, then clay, glass, then some kind of a polymer, new one. Okay, insulators are made up of polymers. Now we can look at the different types of insulators. What are the different types of insulators? The different types of insulators are, first type is a pin type insulator. Okay. So pin type insulator is something that we normally see on the on an electric post. Okay. So something like this, there will be one like this, then you draw like this, then there will be something like this. I hope you have seen this kind of a insulator on the top of the post. Okay. If we look at the top of the transmission post, you can see something like this. This is known as a pin type insulator. This is actually pinned in that particular post. Okay. So if you see a electric post like this, you can see this pin type insulator here. Okay. That will be pinned with this particular T section. So you can see that kind of a thing here. With this, then it will be like this. So this kind of a thing you can see in there. And on the top of this, we will be having this line. Okay. This is something known as a pin type insulator. Then there is known as a suspension type insulator. Suspension insulator. Then the third one is known as strain insulator. Just remember these names, they might ask what are the different types of insulators. Then shackle insulators. These are the things what you have to remember. Okay. So pin type insulators are used voltage up to 33 kV. Okay, this is very important. Pin type insulators are used for voltage up to 33 kV. Above that, we will use suspension insulators. Okay, so you can see a lot of suspension insulators. If you go to very high voltage transmission line, you can see something like this. Like a lot of actually things are suspended on the lines, right? So some suspension insulator. Okay, so these things you should remember. Okay, so these are the different types of insulators. Okay, there is something also insulation string. Okay, like if you go to very high transmission line, you can see something like a string of insulators. That is, a lot of insulators are actually coupled together and keep for the. So okay, so we have 7 more minutes, and we can actually look at the what are the other aspect of an insulator. Okay, that is, if you consider an insulator, right, like this. So the current, this is the nearest ground. Okay, this is where the tower is. So the current has to travel from the higher potential to lower potential, right? So we can see that the current actually see here or there. There is a nearest ground is this, but there is a huge insulator there, so it cannot actually travel through this. So it will actually continue to travel through this. But assume that there is some kind of a conduction path is here. Okay. Then what happens is that the tendency of the current is it should reach the ground. So the nearest path is actually only this length. This length is basically known as the creepage length. Right. So the one way to, so if there is a creepage length is there, then it will cause a single line to ground fault or a flashover. Because the flashover of this particular insulator, and there will be a huge potential difference across actually coming here, and large current actually flowing through this, and this causes a damage to the insulator, right? So the flashover should not happen, right? So that is the most important part. So we have to actually clean the surface everywhere, like that. There is something known as the, we have to protect this insulator to avoid the flashover. Okay. So what are the different cases of puncture is that if there is some kind of an impurity on this particular thing, then this might cause puncture in this like flashover in this particular one, or like what happens, there's a bulk conduction. Bulk conduction is not practically possible, but if that happens, then this also causes flashover. Okay. So in order to avoid this particular flashover, what we use is something known as an arcing horns. Okay, like these things I have already explained. So what are the difference between pin type and suspension type? Okay, with this we can end today's lecture. Then we can look at the some calculation is there how we can actually use for grading of the insulators. Okay, that we can actually check tomorrow. So this is up to less than 33 kV. Sorry, less than 33 kV. This is greater than 33 kV. Okay. So the cost is of pin type is very large if the voltage increases. Okay, that's why we are using mostly suspension. So it almost contains one porcelain disc. One porcelain disc. This contains more than one porcelain disc. One porcelain disc. Okay. Suspension contains more than one porcelain disc. So if that one particular disc is damaged, this is almost useless. If that particular one is damaged, still there are more numbers, so that actually it will continue to act as an insulator. So these are the things you should remember. What are the difference between a pin type and a suspension type? So what you normally see in the low voltage distribution of near your home, that are basically pin type insulators. What you see in the large tower, what that is basically suspension type insulators. Okay. Now tomorrow we will look at the voltage distribution. Like assume that there are three. This is something like this. This is some V volt and this is ground. Okay, something like this. This is the okay. We can draw the opposite way. This is V volt and this is ground. Whether the voltage distributed this uniformly. This is something like V voltage is here and this is ground. Okay. So is it uniformly distributed like this? Or is it something like this? Or is it something like this? Where is the higher potential coming? And this is something like this. Or the most of the voltage is concentrated near this end. Or most of the voltage is actually concentrated at this end. So these kind of things we have to find out. That's why assume that if almost all the voltage is actually coming across this, when what happened? This will actually get a flashover, right? That means there is no presence of this. That means now the current is actually here. Then this will cause flashover of this. This will cause flashover like that. So the series one by one, all the voltage get damaged. So that means we need to get the potential will be almost uniformly distributed, right? So from 1 to 0. So that the potential is uniformly distributed and the electric field will be constant between all the things. Okay. So we have to find out whether this is uniformly distributed or not. That we can do the next class. Okay. So for the time being, we are stopping our class now and we can meet in the next class. Thank you. And you should remember all these things because I'm concentrating more on the theory part now because I'm not doing much on the numericals. So after finishing this transmission thing, I'll be doing some small numericals. So until now, we have to concentrate more on theory because this is more concentrated on interviews and other technical things, not so concentrated with the gate. If it is for gate, I would have done more number of numerical problems. So since it is not concentrated to gate, actually we can looking more on the theory part than the numericals. Okay. So thank you. We can actually stop here now and can meet in the next class.